So let's start with the next session, and Misha is going to not tell us about membrane actin interaction, but he will tell us about curvature effects.
I start my talk this way for the following reason. The title of my talk underwent evolution over a couple of months. The first title was set by Rudolf and Rudy, and it was interaction between actin cortex and the membrane. I started even to prepare it. And 2 days before leaving here, I discovered that it changed to shaping of the endoplasmic reticulum. I was sort of happy about it, but still I would like, I like what I already prepared, sort of prepared the first talk, and it's pity to drop it completely. So that's why I will show you 2 slides, just to let you know that we are doing these things in my group, and if there will be any questions or will to discuss it, I will be happy during the next week. So what we did along the lines determined by Rudolf and Rudy is the following. we considered interplay between membrane and actin cytoskeleton in the course of cell motion. And the first part of it was a sort of an analysis of what is going on mechanically in the membrane of a cell, which moves under pressure, as you know it, of course, exerted by actin filaments polymerizing against the leading edge. We analyzed a very interesting phenomenon, which was probably presented by Eva Paluch in the beginning of adhesion-independent friction-driven motion of the cells, and we were able to show that the direction of this motion and also the speed of this motion depend on the different on a parameter which characterizes a friction coefficient between the anchors of actin cytoskeleton in the membrane as compared with the substrate, as compared to the friction coefficient between the membrane itself and the substrate. And we were able to show that this motion will proceed in forward direction if the friction coefficient of anchors is larger than that of the membrane, and it can even, but this motion can proceed even in the opposite direction if the relationship between this coefficient is opposite, meaning that the friction coefficient of membrane is larger than that of the anchors, which was a sort of surprise for me. So we did it, and as a byproduct or maybe a product of the same calculation, we were able to calculate the tension in the membrane generated by these anchors moving retrogradely together with the actin cytoskeleton. We were able to show that in a fluid membrane, because of this motion, the tension is inhomogeneous. There is a gradient of tension from the front towards the rear of the cell, and Kinneret Keren and her student Arnon Lieber, they measured this gradient of tension, and so we had such a story about tension gradients in membranes of moving cells. This is what we did, and I will be happy to discuss it. And what we did in terms of influence of the membrane on the cytoskeleton, we did it with Tom Shemish and Sasha Bershatsky a couple of years ago, is an analysis of actin organization in the lamellipodia in the front of a moving cell as a result of interaction with the membrane. And there were some interesting effects we were able to describe. Specifically, focal adhesions were also a part of the story, and we were able to describe the peculiar patterns formed in the actin network as a result, in the retrogradely moving actin network as a result of this interaction. So this also quite a piece of work, few papers. I will be also, and Sasha probably, happy to discuss it if anyone has interest in it. So from here on, I will switch to the current topic, to the last topic of my talk, which also somehow was generated, I think, without any help from me. It somehow emerged. And this will be about statics of membrane, about equilibrium membrane shapes in relation to one of the major cell organelles, endoplasmic reticulum. So I will go slowly through so that everyone understands, not only physicists and mathematicians, but also biologists and vice versa. And this work was done through a real interdisciplinary collaboration with a large amount of people. Tom Rappaport was the major biologist who stimulated this work and who provided the major experimental results and experimental findings, who actually asked me for theoretical or for understanding of what is going on in terms of physics, and this drew the whole work. Tom Rappaport is at Harvard, a cell biologist. The major experimental results I'm going to show you come first of all from Mark Terasaki. He is in Connecticut, and from people coming from Tom Rappaport's lab: Robin, Yoko, Junji, Fabian, and Sonyu. Most of them already left. These two guys are still around, I think, at Harvard. And the theoretical work, the theoretical computations were done at the first stage by Tom Shemish. Sasha already mentioned. Tom was a graduate student of mine, then he was postdoc with Sasha, but we kept collaborating, and now he is a new faculty at Technion in Haifa. And Jonathan Schweitzer, he was in my group, a student. Unfortunately, he finished his PhD and unfortunately left the lab for a postdoc. But we still try to keep collaborating. So this is the team. Now, what are we talking about? We are talking about the endoplasmic reticulum. Endoplasmic reticulum, you may know that biologically that this is a place where proteins are synthesized, many of them, and also lipids undergo biochemical transformations and synthesized. And after this synthesis, proteins and lipids leave endoplasmic reticulum as vesicles and go to different goals within the cell. But what will interest us today is not the biological or biochemical function of this organelle, but rather its shape, which is very, very complex. So what you see here is more or less bright spots and lines is the endoplasmic reticulum. Endoplasmic reticulum is a complex, very complex membrane network which starts from nucleus. Actually, endoplasmic reticulum is connected to the outer nuclear membrane. You know that nucleus has two membranes, so it is a sort of extension of the outer nuclear membrane, and then it branches. It branches in all the directions, and what we want to understand is basically the factors, this geometry and the factors, meaning proteins, basically factors and forces which determine this topologically complex and also very, very strongly curved geometry of the endoplasmic reticulum. So in the first, so if one faces as a physicist such a crazy system, one wants try to first to dissect it into the elements, the simplest possible elements it consists of, and then understand first of all what is needed in order to generate these elements, and then go to further to structures built by these elements, superstructures, and so on. So to go from simple to complex, this is the only way, in my view, to understand such a system. And this is what can be done. This is a sort of course, personal how one does it, but I did it for this presentation, at least in some way. And it looks the following. First of all, there are tubes and sheets. So there are two elementary structures of the endoplasmic reticulum, tubes and sheets. Tubes are tubes. This is the image, fluorescent image. The tubes are characterized by their diameters. This is the most important characteristic. And in yeast cells, the characteristic diameter is 30 nanometers of ER tubes. In mammals, it's 50 nanometers tubes. So sheets are, they are 50 nanometers wide and microns long. So there are really thin tubes. And sheets are such flat cisternae which have edges. So the sheet is basically flat all over its surface, but it has edges. The thickness of the sheet is the same, equal more or less to the same 30 to 50 nanometers. It depends on you. I mean. Okay. Okay. So it's a sort of a background. Background is good. So the thickness of the sheets is the same 50 nanometers for mammals as thickness of the tubes, and the sheets are also microns wide, from micron to several microns in this linear dimensions. This is an image of the sheet. So this is the first thing we have to understand. Sheets and tubes. Please remember this number, 50 nanometers. This number determines the curvature, basically, the curvature of the tubes and the curvature of the curved parts of the sheets, their edges. Second thing, superstructures. I would like to classify two types of superstructures. First is made of tubes, and this superstructure is basically a network made of tubes. Network is first of all characterized by junctions, right? So junctions, this is what characterizes the network. So a characteristic feature of this ER networks is a three-way topology of junctions. One sees only three-way junctions. One never sees four-way junctions and so on. So three-way junctions, this is what characterizes the networks of ER tubes. And sheets are often a part of these networks. There are junctions between tubes and sheets in addition to three-way junctions between the tubes. And these junctions are, if you like, T junctions, T-like junctions. But what is a common feature of this and these junctions? If one looks, we will see it in cartoons, but you can imagine that a characteristic common feature is this thing, these corners, and these corners mean that the membrane in these corners has a shape of a saddle-like shape. It is bent in this direction. If we can determine this curvature of this line as negative, and in the opposite, in the direction perpendicular to the plane here, is positive. So the shapes are that-like, saddle-like shapes. So generation of these saddle-like shapes, in addition just to tubes, cylinders, is a feature of generation of these networks. And another two types of superstructures are related to sheets only, without tubes. One of them is fairly simple, is represented by holes, by perforations within the sheets. What is important here is that these perforations are large. I hope I will have time to explain you the essence of it. They are large. They are of the same order of magnitude as the sheets themselves. They are not small. They are not in the scale of tens of nanometers like thicknesses of sheets. They are huge. This one. And the second kind of superstructure is much more delicate. This kind of superstructure was discovered by Mark Terasaki, who did ultra-thin sectioning of ER stacks. And the essence is the following. Let's first start from this picture, which represents a cross-section of stacks of ER sheets, which happens in, you know that this is called rough endoplasmic reticulum. You may know that one classifies endoplasmic reticulum into smooth ER and rough ER. Smooth ER looks smooth and basically consists of tubes, and rough ER is represented by stacks of sheets with ribosomes sitting on them and between them, sitting basically on the sheets. Polysomes, polymers of ribosomes or monosomes, most of them sit on sheets and generate proteins, synthesize proteins. So the major synthesis of proteins happens in the rough ER. So rough ER is very important. It fills professional secretory cells, such as salivary gland cells, for example. They are full of stacks of ER, and this is a cross-section of one of them. These things are not tubes, they are cross-sections of sheets, right, with ribosomes sitting here. So it seems like a regular lamellar structure. What Mark discovered by thin cross-sectioning, fine cross-sectioning, I mean the distance between sections were about 30 nanometers, the same as thickness of a sheet. Before one used 50, 60 nanometer sectioning, and one didn't see this structure. And Mark Terasaki was able to see this kind of structures, such as termination of sheets, holes in sheets, and also junctions between the sheets. The ends, I will show you a more detailed picture. This is one of these places. We call it sometimes Terasaki motif, which was found by Mark. It is the following. Look here. We have one continuous sheet. It goes through the second continuous sheet and an edge of a sheet. This is the edge. In the next section, this edge, we see this edge closer to the continuous sheet. In the next, it fuses with the continuous sheet. This three-way junction-like structure. It's not a real three-way junction because we are talking about surfaces, not about tubes. Exists for a couple of cross sections, and then another branch separates from it, and goes away. So this is a Terasaki motif, and this movie represents the Terasaki motif, evolution of Terasaki motif. But I want just to stress that what you are going to see is not a time sequence, is a space sequence, one after the other. So, and we will see how it looks like. Pumps. So those are the evolution of the Terasaki motif in cross sections. So the question people come to us. Yes, please.
Do I have really? I mean, you said it's 50 nanometers. That means that basically I have two monolayers, or how do I?
The thickness is 50. The thickness of a sheet is 50 nanometers. The thickness of a membrane is 4-5 nanometers.
Let's say so. I have
two membranes. Yeah, it's a flat cisterna, okay, with the edge which is bent with 25 nanometer radius, and and distance between. So this is a Terasaki motif, exciting thing which excited us a lot. So yes.
How closely have people been able to follow the initial evolution of these sheets following nuclear division?
Initial evolution in which sense?
Are these sheets laid down on top of each other? Are they somehow?
It depends. There are dispersed sheets. We are talking about cells. We are not talking about engineered structure. So there are cells which have a relatively small amount of sheets and mainly tubes. In this case, as I shown in the first, the sheets are often just integrated in tubular network and don't face each other. In cells which are specialized in secretion, such as salivary gland cells, they are full of sheets, and then the sheets are stacked. And one actually didn't know. I will tell you in the already what I will come to at the end. It was thought that the sheets of the stacks consist of independent sheets, just lying one on the other, and it was unclear whether there are connections between the sheets. For example, in other biological example are Golgi stacks. In Golgi, we know that there are connections between cisternae, and that cisternae can work as one unit due to this clear connection. For ER stacks, it was unknown. So what we were able to show in this study, the combined experimental theoretical study, that these defects represent actually, in lamellar packing, represent actually cross sections of connections between the sheets, so that the sheets are connected to each other. And if they are connected to each other, this means that proteins and ribosomes can travel through the stack, giving, theoretically at least, a possibility to the stack of sheets to work as one unit, not as separate subunits. Yeah.
Is there some functional advantage to having them stacked in sheets, or?
Yeah, I mean, exchange between sheets. But as compared to Golgi stacks, in Golgi it is known that there are matrix proteins which somehow seem to also to exist between the cisternae and to hold them. For about ER sheets, it was unknown. At least no one saw these proteins. Probably they don't exist. And these connections, we calculated it theoretically, they are able also to hold the sheets at a well-defined distance one from another, meaning to structurize, in a sense, these stacks. Yes, Leah?
Is there a three-dimensional picture of?
Right. We generated. This was, I will show you, this is what basically, concerning this Terasaki motif, our task as theoretician was first to realize what is a three-dimensional geometry which gives these cross sections, and second to rationalize generation of these structures in terms of physics, in terms of simple physics, basically in terms of membrane elasticity. This what was done. So in general, what the goal of all this big project was to understand physical mechanisms behind all morphologies seen in the endoplasmic reticulum and understanding their origin, physical origin, and specifically understanding of this non-lamellar motif in stacks of ER sheets. This was the goal, and I'm going to show you how we approached this problem in a historical evolution, because I think that it's easier to understand if one follows the development of ideas. The talk is relatively long. I can do it. So where the problem comes from? The problem, first of all, the origin of the essence of the problem is the membrane curvature, because as I already tried to stress, is that the elementary structures, tubes and sheets, they are strongly curved. The tubes are strongly curved, and the rims of the sheets are strongly curved. When I say strongly curved, what does it mean? It means that the radius of curvature of membranes there, which is about 15 to 25 nanometers, depending on the cell, is not much larger than the membrane thickness, which is about 5 nanometers, meaning that the ratio between the thickness, membrane thickness, and the radius of curvature is just 0.2. I mean, the radius is 5 times larger than the membrane thickness. The radius of curvature couldn't be possibly be smaller than the membrane thickness, meaning that if it is more or less of the same order of magnitude as the membrane thickness, this means that the curvature is large. So this is a major characteristic, large curvatures of these structures. I prepared some introduction into curvature, but due to Alain's lectures today, I don't need to do it. Okay, so I just shortly repeat that the membrane has to be described by one. In order to describe the membrane in terms of curvatures, first of all, one has to choose a plane, with a representative plane within the membrane. We did a lot of work on it. It's called neutral plane, but in short words, for a bilayer, symmetric bilayer, a neutral plane just lies in the middle of the membrane. So this plane represents the membrane shape at every point, and the shape, local shape of the membrane is determined by two numbers. These numbers can be two principal curvatures, or they sum and product, which are called mean curvature, or we call it total curvature. The difference is just a factor of 2. And the product, the physics of membrane is described by these two. Not by principal curvatures, but by these two numbers, because these numbers are scalars of this curvature tensor. Right? I don't have to go into this detail. It was very nicely presented in the second lecture today, this morning. So I will skip it. And very shortly, the Helfrich model, which was also already mentioned in full detail, gives us the possibility to compute energy related to membrane curvature locally at each point of the membrane. In order to calculate the total energy, one has to integrate this thing over the membrane surface. And there are basically 3 material parameters of the membrane which determine membrane physics in this respect. They are bending rigidity, which is a real rigidity, and 2 parameters which are basically forces, stresses. One of them is spontaneous curvature, which represents, believe me, I don't have time and an intention to go into detail because we had it already today. But in few words, the spontaneous curvature characterizes a bending, intrinsic bending moment, which exists in the membrane as long as the membrane is flat. I heard a lot, I thought a lot in my life about this, so believe me, this is what it is. So if we take the membrane in the flat state, and it is, because of its asymmetry, it is stressed, and there is a bending moment, it is characterized by the spontaneous curvature. And the second bending moment, which is a more delicate thing, is characterized by so-called modulus of the Gaussian curvature. The modulus of the Gaussian curvature is not a real modulus in the sense of membrane elasticity. It is stress. It's a second moment of distribution of local stresses through the membrane thickness. Doesn't matter. These 3 things are important, but for us, only the bending rigidity today will be important, because we are not going to talk about the changes of membrane topology where this contribution works. We will consider symmetric membranes with vanishing bending spontaneous curvature. So the bending rigidity is important, but as a physicist, not a mathematician, you are interested in numbers, right? In order to know, and so Anna already mentioned KT as a measure of thermal energy, and so it turns out that the bending rigidity is about 20 kBt. What does it mean? 1 kBt, as Anna already mentioned, is a unit which can be is a characteristic energy which can be provided by thermal fluctuations, meaning that if the rigidity would be equal to 1 kT, the membrane wouldn't be able to maintain shapes. The shapes will be smeared by thermal fluctuations. But a membrane has bending rigidity of the membrane is by an order of magnitude, by 20 times larger than KT. This guarantees an ability of a membrane to maintain specific shapes. And due to this, this keeps us employed, so we can study these shapes because they exist. And this is due to 20 kT bending rigidity, and as I said, the total energy has to be computed by integration of local energy density over the membrane thickness. Now,
may I ask a question?
Yes.
And maybe you are coming to that anyway, but usually as a physicist one thinks of such an Hamiltonian of being just an expansion of some true function. And this is what we can measure now. The curvature is pretty high in this
right,
system.
right.
Are we coming away with just using
More or less. I mean, we still have an. Yeah, this is a good and very common question. With a good. Well, again, from my experience, in general, Rudy is absolutely right. If the radius of curvature approaches the membrane thickness, we may want to have higher order terms in this extent, because this is an expansion in the parameter, which is the ratio between the membrane thickness and the radius of curvature, basically. And we retain here only quadratic terms and don't account for higher order terms. But I worked at some stage with on treating experiments with very highly curved membranes, such as membrane in H2 phases, if you know what this is. And it turns out, de facto, that membranes are fairly linear.
Wow.
Meaning that one can very what would mean high order terms? It would mean that these material parameters would depend on the curvature beginning from something. So one can neglect this dependence for fairly large deformations. And at least semi-quantitatively, it gives us, for this inverted hexagonal faces, it was amazing how linear the system is, because the radius of curvature, because of inversion, were even smaller than the membrane thickness sometimes, or equal to the membrane, 3 nanometers. And a linear theory still worked de facto. The curves, stress-strain relationships measured by Peter Rand at that time were linear, straight lines.
Is that because of the
Voila.
apparent fluidity of the membrane?
Fluidity is mostly in the lateral direction, and as far as the curvature is concerned, we are more talking about transverse direction. This deformation of bending can be seen as a shear in transverse direction. The shear modulus in lateral direction is 0, but shear modulus in the transverse direction is not 0, and this bending elasticity can be translated. So probably it's fluidity, hence I don't know, but this is the fact. So in a few words about how this curvature can be generated, we are talking about,
One question is why I would expect that a wheel at this highly curved places still have a symmetry in the bar layer. So J naught term.
Asymmetry.
Yes, that I will have a spontaneous curvature.
Yeah, you could, but we don't have any indication that this is the case, and as long as we don't have any experimental indication, we go for simplest. Of course, the membrane, every membrane has different lipid composition of monolayers and so on, but which could be a reason for generation of this curvature. But what we think is that this curvature, large curvature, is generated by proteins, and I'm going to talk about these proteins. And this brings me to this slide. Well, we are thinking, this is also a sort of a area we are working on in general. We are thinking about mechanisms of generation of large curvatures by proteins. There was quite a discussion in the literature during the last years, but we are thinking about two major mechanisms by which proteins, or more exactly peripheral proteins, can generate membrane curvatures. And these mechanisms are fairly simple. One is, we call it a hydrophobic insertion mechanism. It's based on insertion of a small hydrophobic domain shallowly, basically between the polar head of lipid molecules. This generates the maximum asymmetry in the monolayer, in the upper monolayer of the membrane, And there are classes of proteins which have so-called amphipathic alpha helices, which go shallowly into the membrane. If they would go further into the membrane, it wouldn't work. So I even have a slide on it, but I don't have time to talk too much about it. The bottom line is the shallow inclusions generate large curvature. And the second mechanism is a scaffolding mechanism. Yes, please.
Would it also be possible to get a curvature by hydrophilic insertion?
No, hydrophilic, yeah, this is in a sense. So the scaffolding mechanism, no, hydrophilic insertion, yes, those are two contrasting words. Hydrophilic particle doesn't go, it doesn't insert, but it can stick. It can stick to the membrane, for example, through electrostatic interactions. Lipids are negatively charged, proteins are often positively charged and stick to the membrane. If the protein is which sticks to the membrane by this electrostatic, for example, electrostatic mechanism, has an intrinsically bent shape due to its structure and is sufficiently rigid, meaning that more rigid than the membrane, and its energy of sticking of attraction to the membrane per unit area is larger than the membrane rigidity, then such scaffolds can bend membrane locally, and this in both cases locally induced curvature propagates to some extent along the membrane area due to membrane bending elasticity. And these guys can generate membrane curvature locally. Example, most obvious example of insertion having proteins inducing membrane curvature are epsins, for example. Also many small G proteins, such as ARF, for example, they have small insertions, and most probably they bend membranes by this due to these insertions. These insertions, in this case, go in the case of G proteins, go into the membrane as a result of in GTP form shape. They can change as a result of hydrolysis. But those are most prominent examples of proteins of this class. And this most prominent proteins belonging to the scaffolds are bar domains. There was a huge literature on bar domains. Has been so bar domains, F bar domains, N bar domains, I bar domains. They all bend membrane by scaffolding mechanisms. N bars can bend both by insertion mechanism, because they are N bars due to N terminal helices they have, and also in addition scaffolding. Yes.
Why did you take into consideration intrinsic membrane molecules? I mean, with synaptic vesicles, it's pretty much the same curvature, or in the junction between the T tubules and the sarcoplasmic reticulum. These are the tetraspan membrane proteins.
We are looking for mechanisms of generation of large curvatures. Meaning that curvatures whose radii are a few times larger than the thickness. In order for membrane spanning protein to generate such curvature, this protein has to have a shape of a cone, which is amazingly curved in itself, such that this cone, the intrinsic curvature of this cone, is as large as we want to have. And to my understanding, there are I don't know examples of membrane spanning proteins which would be structurally so asymmetric that they would be able to generate such curves. It's a question of numbers. These guys can generate very large curvatures we need. And this is what is shown here, in order to show you that I'm not just talking, but we do calculations. We computed quantitatively how much curvature can come from these insertions, and also you will see a little later we computed how much curvature can come from scaffolds, and those are the results of calculations. To compute these things, we couldn't use Helfrich theory anymore, because we are talking about membrane perturbations by particles which are as small or even smaller as the membrane thickness. In this case, Helfrich model is useless. We just can for this calculation we used modeling of the membrane as a thick elastic layer with the elasticity characterizing every point of the membrane as thick as compared to the particle. But the results of this calculation can be used then as parameters of Helfrich model. In this way, we calculate the spontaneous curvature of the preferred curvature of the membrane as a function of the density of these proteins, and taking these numbers, we could, for example, estimate how many of these insertions are needed in order to generate tubes of 50 nanometer diameter, and we got reasonable numbers that about 10% area coverage, membrane area coverage by amphipathic helices is sufficient in order to generate tubes of this diameter, which sort of convinced us that we are more or less okay. We are not talking about phantoms. Yeah, we are talking about real things. Okay, this is just to convince you that we know what we are talking about, hopefully. And now let's go back to endoplasmic reticulum. This was all background. So we want to understand the endoplasmic reticulum curvature, first of all, of endoplasmic reticulum elements, and then the elements, the geometry as it is. And if one deals with biology, one needs first to get some knowledge about proteins in there, because all this is driven by proteins. And here comes Tom Rappaport came in the game. So this was the beginning. Tom Rappaport and his guys published already almost 10 years ago a cell paper on the protein. They discovered the protein which is responsible for generation of ER tubes. These proteins are called reticulums. It's not much is known about the structure of reticulums. What is known is the following: that they have hairpins going into the membrane to some extent. They may lie flat, they may go somehow inside, and these reticulums undergo limited oligomerization on the membrane plane. Oligomers are relatively short, about 5-6 proteins. This is what we think at this stage. Why this oligomerization is limited, we don't know. This is one of open questions we're still facing. But reticulums were proven to be responsible for generation of membrane tubes. It was shown that they partition to the tubes and not to the sheets. It was shown that depletion of reticulums from a cell drives transformation of tubes into sheets, and overexpression drives back transformation sheets into tubes. It was shown that lipid vesicles reconstitute, that reticulums reconstituted into lipid vesicles drive transformation of more or less flat membranes into thin tubes of diameters about 20 nanometers. And this was the phenomenology which convinces that reticulums are indeed the tube generators. So how reticulums can drive curvature? They have attributes for both, basically, for scaffolding due to oligomerization, and for insertions because they have these hairpins. What is the major factor? We don't know, but we are convinced that the scaffolding is a essential part of the story. So the scaffolding mechanism is essential in the action of reticulums, but insertions can also contribute. And the next, so this was known, and we did some calculation on. I don't have a slide on it, but this was the beginning of our collaboration with Tom Rappaport. We did with Tom Shemesh at the time. We estimated how many reticulums are needed in order to generate tubes, because our friends were, on one hand, they were convinced that reticulums drive tubes. On the other hand, they knew that the amount of reticulums in the system is not sufficient far from the amount which would be needed in order to cover the tubes completely by the protein. And we were able to show that the amount, I have somewhere a slide later on, that the amount of reticulums needed can be very small. Up to 5% of area coverage by reticulums would be sufficient for generation of smooth tubes. This is all due to membrane bending elasticity, because if one has some ring-like scaffolds, for example, and constrains the membrane between two rings of 50 nanometer diameter, one can show that even if these rings are far apart, up to 50 nanometer one from other, the membrane in between will remain fairly smoothly cylindrical. The membrane maintains a cylindrical structure. This was the first thing we did, and this was a nice addition to the idea that reticulums generate tubes. The second question I was asked by Tom Rappaport was the following. After having understood generation of tubes, they were interested in generation of the sheets. And the idea was that there are special proteins which generate sheets. Reticulums are responsible for tubes, and there are some proteins which form bridges. These things would generate sheets. Quite a straightforward idea. So I spent the days, I remember, at Harvard and Boston, and they showed me the structures. But what was obvious for me is the following: that if such mechanism would work, we would expect that these edges of the sheets would be very unhappy and would swell, meaning that we would have some discs with swollen edges. At the same time, the edges of the sheets are sharp, meaning that but on the other hand, if something stabilizes the edge, you don't actually need anything in between. The membrane in between the edge, curved edges will remain flat by itself. So, meaning that the primary thing would be to stabilize edges, and these edges could be stabilized by the same reticulums. They didn't see them on the sheets, but the idea was that the edges could be stabilized by reticulums, meaning the following: that reticulums, if they are arc-like scaffolds, they can form tubes, but they can also form edges, and the rest is easy. The rest is easy. So the idea was that reticulums are responsible for both generations of tubes and the sheets, but the prediction was that in this case one should see reticulums on the edges, something they didn't see. So it took 2 years, I must say. As I got an email from Tom Rappaport that this idea may be indeed not only interesting but also correct. That reticulums are on the edges. So those were the first pictures they obtained with green is a reticulum which is decorating the meshwork of tubes, but also the edges of the sheets, like here. This was done under some overexpression of reticulums. That's why it was not a complete proof, but we published it in 2010. During this 5 years, even 6 years, a proof was obtained, experimental proof, that also in normal conditions without overexpression one sees reticulums by super resolution microscopy. One sees reticulums on the edges. So we are convinced that reticulums form both edges and sheets and tubes. And we did some supporting computation, which is a sort of decoration, of course, after one saw proteins there. So, but still, we did the following calculation: assume that we have we change the amount of this edge-generating proteins, reticulums, in the system. And the question is, if we generation of larger and larger amount of those proteins generates more and more edge for the same more or less area of a sheet, and the question was, what will be the structure? Because if we generate the edge, you have excess of the edges compared to the area, And just a moment. And the question was the following: we assume that this edge, while stabilized in one direction, has some rigidity in the second direction, in the direction of the edge line, meaning that the edge could be represented by an elastic line, and so that a straightforward conclusion was that the shape for each given length of the edge would be set by minimization of the energy of this elastic line. There was a question.
Tell us just a few words about the model. So how does it connect with Elfrich? So you have two components.
Spontaneous
curvature.
I will show you.
Okay, so
You have, this is still a sort of qualitative introduction, if you like, because most of people want to understand the essence. But I will show you. We did it all in all detail. So, minimizing the elastic energy of the edge line, we were able to show that indeed, for relatively large lengths of the edge, we get sheets. This is one sheet. This connected by a tube. This was the optimal. I was sure we will get this result because I knew from other calculations in my youth, I mean 30 years back, that this will be the result. But what was a little bit unpleasant is that the sheets were droplet-like, that this transition between the sheet and the edge was smooth, while in reality we have a much sharper transition. This means that we thought that maybe there are, in addition to reticulums which just generate edge, there are molecules like reticulums which also generate edge, meaning that they generate curvature in this direction of the edge, but which influence also the spontaneous curvature of the line. If there would be different, at least two kinds of proteins which generate edge but different intrinsic curvature of the line, such that there would be proteins which prefer negative curvature of the line, and they would partition into this region, they will make a more sharp transition. And few years later, this was relatively recently, about 3 years ago, 2 years ago, we understood that another kind of protein was found, which are called Luna Park proteins, which were shown by Novik's group and then by Tom Rappaport's group. They are green here. They partition into three-way junctions between the tubes. And the three-way junctions are negatively curved here. The line of three-way junctions is negatively curved. This gave us a reason to assume that this Luna Park are this missing kind of proteins which would make the whole story even better in terms of comparison with the structure. I already coming to the model.
Those Luna Parks are somehow similar to Septin, like the same family?
No. I must say that now we are not 100% convinced that we are right, that Luna Park may be, the action of Luna Park may be more, less straightforward. I wouldn't now stick my neck for this model concerning the Luna Park, but I am sure that we are right concerning reticulums. At any rate, Luna Park partitions into this negatively curved regions of the line. So the qualitative idea is that if we have two kinds of edge stabilizing proteins which are different in terms of preferred curvature of the edge line, those which generate flat or positively curved edge lines, they would generate tubes, and external sheet edges, those which generate negative curvature of the edge line, would drive formation of internal edges, pores, and and three-way junctions. So now, in order, so this is basically this model. All of them generate this curvature, which is positive, but some of them generate also positive curvature of the edge line, some of them generate negative curvature of the edge line. And interplay between these two kinds of proteins basically gave us a possibility to explain the whole morphology of the endoplasmic reticulum. Now, so I have 15 minutes, yeah?
Well, 15 minutes before discussion.
Before discussion, yeah. I'm afraid after discussion, but I am a tougher chair. So I chair myself. That's not so. The logics of our work was the following. First of all, to find the physical basics which would justify the assumption of this model, meaning that to find out whether proteins such as arcs interact with each other through the membrane possibly, so that they would line into strip-like arrays, to make sure that these arrays generate indeed sheets, meaning that they bend the membrane underneath and the membrane outside would form a flat sheet with two parallel flat membranes, and that they could generate, depending on their structures, these arcs could generate edge lines with positive and negative curvature to show this, and then based on that analyze the morphologies. So the few ideas, so my time is running, is the following. We modeled the scaffolds as patches, basically membrane, arc-like membrane patches with one curvature, this one, corresponding to the curvature of tubes and sheet edges, meaning 25 arcs with 25 nanometer diameter. But this transverse curvature along the short direction in this arc is a free parameter. It could be different. It could be different depending on the membrane, on the structure of the protein. For example, insertions would generate positive curvature in this direction. Depending on the insertion, the value of this curvature could be different. So this is the model for the arcs. And first we considered interaction between two such arcs on the membrane. We talked with Charlie in a little bit more detail about it, so I don't have time. But the idea is the following. The idea is not new. The idea is the following: one such arc on the membrane deforms the membrane around, and this deformation propagates all over the place. This can be computed based on Helfrich bending energy. Simply we did it numerically, this computation by surface evolver. The boundary condition between the insertion and the membrane was the smoothness of the profile. That's it, only this. Now, when one puts two such insertions on the membrane, deformations they generate overlap, and this drives interaction. This drives two kinds of interaction. First of all, interaction of orientations, and also attraction repulsion interaction. This kind of things.
Is it always in repulsion?
No, no, it's not. So there is a prehistory of this, and I was a part of. In '96, we published a paper on it. There was in '90s, there was a bunch of papers concerned with membrane-driven interaction between insertions, but they all of them were done in approximations, like theoreticians like doing it, for small perturbations, meaning for flat particles far from each other. As I said, I was a part of, I was at that time with Wolfgang Helfrich in Berlin, by the way. That was my last year. So the bottom line is the following. If the particles are axially symmetric, they repel each other. If they are asymmetric to some extent, either they have asymmetric shape, elongated shape, or they have different curvature in two directions, then they have also an attractive component of interaction, but the repulsive component is also there. And as a result, we get the following. For the major goal of our calculation was to check whether if the particles which simulate or which illustrate realistical proteins, which are as long as bar domains, for example, and as curved as bar domains, whether they interact and what is the energy of the interaction, because all this analytical calculation gave energy of the order of kT, 1, 2 kT, which is unfeasible in terms of clusterization and so. My feeling was that if one takes a large particle like reticulum oligomer, which is 10 nanometers or 15 nanometers long, one gets more energy, which is more or less obvious. So we did these calculations, and we found that asymmetric particles attract each other at long distances, and the repulsion comes into play usually at short distances, so that one has always an energy well. And for proteins, for realistic proteins such as bar domains, we did it for bar domains. This well is about 50 kT.
And that's average over all orientations?
No, it's not average. They first orient themselves. They first orient themselves in such a way that they face themselves by the direction of smallest angle, weighting angle, and then they attract each other. We did also estimation of the effect of fluctuation of orientation, which gives repulsion, but this repulsion is relatively weak. So this was the first to your question. This is the first step towards justification of the model, and the second we took, based on this result, we assumed that we have a linear array. I must confess here that we didn't perform this analysis for many scaffolds. We did it only for 2 scaffolds, and we know that these interactions are not additive. Many particles will interact differently, but the hope is that qualitatively the interaction is the same, and there is a support coming from simulations. Basically, there were a couple of works on simulations by a couple of groups which basically support this assumption that due to this membrane-mediated interaction, this particle can form linear arrays. So now what we do, we assume this linear array, and we ask what will be the distance between the particles within this infinite linear array, what will be the preferred shape of the edge line, and what will be the preferred shape of the side view, whether the membrane coming out of this array, 2 membranes, will be parallel and flat, or they will go apart or cross each other, and so on. So this is what we did with Jonathan Schweitzer and also Tom Shemish, and what we got is the following: that this flatness of the sheet requires that these arcs are close to hemicircles. If they are smaller or much larger than hemicircles, then we won't have flat sheets. So these arcs may be a little bit over semicircle. This guarantees flatness of the membrane sheet. This one requirement of prediction, if you like, theoretical prediction. And the second is, yes, I am talking 1 hour. I'm going. And the second prediction was that depending on this transverse curvature, the distance between the particle is different, and also the curvature of the edge line is different, so that there are 2 regions along this axis. I was supposed to have this transverse curvature of the arc, and this is the curvature of the edge line, and the curvature of the edge line can be positive or negative depending on the transverse curvature of the arc, which gave us a sort of support of our assumption that arcs can generate different proteins, different arc-like protein or protein oligomers, better to say. They can generate edge lines with positive or zero or negative curvature, depending, in this case, on the transverse curvature of this arc. And we also calculated the bending rigidity of the edge line, meaning that the rigidity characterizing the energy of deformation of the edge line with respect to its spontaneous curvature. Right? This was all calculated numerically by using surface evolver, and this is so, of course, it goes back to the membrane rigidity. So because we model in all detail the membrane between the arcs, and the membrane has bending rigidity 20 kT, and based on that we calculate the effective bending rigidity of the edge line. So my time, I have to finish. So what we got then is the following. We generated a phase diagram which tells us the following: what will be the shape of elements of endoplasmic reticulum depending on the following two parameters, depending on the total amount of the edge generating proteins per unit length of the edge, and the ratio between the proteins which generate negative curvature of the edge line and positive curvature of the edge line. And we got a phase diagram. Tom Shemish did these calculations. De facto is the following: that depending on these two parameters, we can have either unbranched tubes if the amount of this curvature generating proteins is large, independently on whether they are negatively or positively curved, if you like. If there is an excess of these proteins, we have always tubes for the following reason: there is no area left for sheets or three-way junctions. If the total amount of these proteins goes down, then we can have either three-way junctions, meaning networks of tubes, or networks of sheets and tubes. This depends already on the relationship between these proteins and these proteins. And if we have a small amount of these proteins, we can have fenestrations, which are actually not real holes in sheets, but rather spaces left between the sheets which come together and are connected to short tubes. And in here we have this helicoidal stacks. So I will skip, I will go very shortly. We modeled the structures in every domain of this phase diagram. Those are the tubes. We modeled those are the tubes experimentally. Tom Rappaport and his guys did experiments based on the predictions of our theory, and this is what they got under huge overexpression of reticulons in this case. Basically unbranched tubes. Under the conditions here, they got indeed dense networks of tubes with three-way junctions, and one could even, this was the theoretically predicted conformation of three-way junction, and this was a super resolution microscopy of a three-way junction. In this domain of the phase diagram, we had sheets, we predicted sheets with tubes emerging, many tubes emerging from the sheet edge. And this was the theoretically predicted conformation. This was a super resolution, again, which in our view more or less demonstrate this structure. One couldn't hope for a better. This is the fenestration regime where we predict sheets connected by short tubes, and these holes seen as fenestrations. This is an experimental picture for that. And few minutes I will spend on this, on what I started with, on this Terasaki motif. Our conclusion was that Terasaki motif is given by helicoidal structures, but hollow helicoidal structures. helicoidal structure. This is this shape of a flat of a plane, which is so spiral-like, and the hole in the middle is a spiral. So the hole is the edge, which has negative curvature. It's an internal edge, and this thing, this shape of a helicoid, this is a shape with zero curvature, with zero mean curvature. It is a so-called minimal surface. In terms of bending energy, it is as good as a flat plane. The problem, so we were happy to understand it, and and indeed cross sections of such a helicoid very closely reproduced this Terasaki motif. Those are theoretical, numerical cross sections, but they are very similar to the Terasaki motif we just saw. A little problem was to see how to bring these helicoids into one array as an experiment, but because it was clear for us that once we try to bring them into one array, they will deform each other and they will deviate from this nice minimal curvature thing. But it turned out that if we take right-handed helicoids and left-handed helicoids and peg them into such a checkerboard structure, this frustration will be minimal. And we were so we did it. Tom did it numerically with this interstices between them. These interstices are always pure saddles, meaning no curve. There was a few weeks as Tom was trying to convince me that there is no curvature at all, but I felt bad about it, because I knew that if this would be the case, this would be a minimal surface, and people would know about it for at least 200 years. But then, to my relief, it turned out that it was a small bug in computations. There is some energy. It's not quite minimal, but the energy is small, and this energy drives repulsion between these helicoids. But the prediction was that in real systems we should expect more or less equal numbers of right and left-handed helicoids, and then this Tom Rappaport's guys computed it, and indeed it was more or less roughly equal, right and left-handed helicoids in the stocks. And this is I am finishing. This is a theoretical prediction of such array. It should turn, yeah, of such array. This is a theoretical model. Those are the theoretical cross sections of such array of helicoids, and those are experimental cross sections, which are again fairly similar. And those are 3D reconstructions Mark Terasaki did after we came up with this prediction. Before, he claimed that all these programs for 3D reconstructions, they're all just misleading. What happened then, that Tom Shemish started to generate his own software for for 3D reconstruction, which was of course not so good. But then it turned out that there are commercial software, and Mark did this reconstruction and found this left and right-handed helicoids in real system through this 3D reconstruction of his cross section. This is one of this is already a 3D reconstruction of taken out of a stack. So conclusions, I think, are obvious. I thank you for your attention at such a late hour. Thank you very much. And
yes, it's happy. I mean, I think we can have some questions. I mean, again,
I will be happy.
Misha, nobody did such reconstruction for Golgi. Actually, as far as I know, there is no such.
I don't know. I know that Jennifer Lippincott-Schwartz was very excited by this ER work, and she met Tom at Woods Hall 2 years ago, and she had this idea that something similar should be in the Golgi, but I don't know whether it was somehow realized.
So, do you think the cell can control the ratio of the two proteins in different parts of the cell? So as to get lots of tubules somewhere and then lots of sheets somewhere else, or not?
I hope so. I hope so. But in general, even if the total ratio is controlled by the cell, this is already enough for us, because then the system will. What we have here is basically phase separation of a system into tubes and sheets. And if this phase separation happens, then we have all what we need. But what we do take into account in the model, that these different proteins, they do separate along the edge. They separate through membrane-mediated interaction, which is counteracted by entropy, of course. But it is more or less effective, so that there are enrichments of different regions in different proteins. Okay.
So back to one of my original questions, this thing looks like a radiator. So is the system trying to maximize or increase area and diffusion between the fins, as it were?
Maximize area. I mean, the area is the total area is fixed by the amount of liquid provided. In changing the area, this is not. It's not a system under surface tension. It's not.
No, but I mean in evolutionary terms.
Evolutionary.
No, why did it develop this system that looked like a radiator again? It must have been
it looks like a radiator. You mean this stack of sheets? This happens in a specific types of cells. They call it professionally secretory cells, where the goal is to enhance secretion as much as possible, meaning that they have to have this as much as possible of this rough endoplasmic reticulum. And but it doesn't happen in all cells. In cells which are not interested in it, we have this, meaning that nature can control it. It does control.
Is it possible to show that that's the most efficient packing under certain constraints, like you cannot get more than 25 kT energy, right? Could you generate other geometry, 3D geometry, that would put more membrane in a given volume?
It is definitely, because in this case what we need is as much area as possible and as little edge as possible. And of course lamellar structure, which is limited from the sides, is the most efficient in terms of proliferating the area. In this sense. And as I said, these connections, they set the distance between the sheets, because this is what we could calculate. We could compute the optimal pitch of these helices, and how this optimal pitch depends on the protein composition. And the results were reasonable in terms of comparison with images, with pictures.
Kind of philosophical question. Actually, you calculated the whole structure at once, okay? But when cell begin to build it, it build it from something which is much smaller. So is such structure are kind of optimal at any step, or the cell in a way kind of do it by some rules, and as a result you obtain...
Actually, we didn't calculate the whole, we calculated the elements. We take an element with a given ratio between the edge length and the area of flat cell, and we calculate the conformation of an element. This is like mosaic elements. Out of in this sense, from the beginning. If we have from the beginning the same relationship between the area and the age, meaning that, in other words, relationship between the amount of lipid and protein. then we are supposed to have this. If this parameter changes, then we can have the corresponding structures.
Are these surfaces closed?
Yes.
There's an interior and an exterior.
I mean, the overall surface of endoplasmic reticulum is supposed to be closed. It is dynamic. I didn't say it because the tubes, for example, they undergo fission and fusion all the time, and there is a protein, at least one atlastin, which is responsible for fusion, and we don't know what is responsible for fission, but maybe it's spontaneous. But this is a dynamic structure, but it is closed. It is closed with a crazy topology. I mean, genus of this thing is absolutely, I don't know what it is, but it is closed, yeah.
Sometimes could be shortcuts with plasma membrane, isn't it?
There are, I think that there are works on contacts between ER and plasma membrane, ER and Golgi, ER and mitochondria, and one says that in this is Gia-Wölz, for example, ER mitochondria, and there are works speculating, and I am a part of one of them with Jennifer, where it is claimed that mitochondria fission happens under the contact with the endoplasmic reticulum, where a tube of endoplasmic reticulum surrounds mitochondria, forms such a loop, and mitochondria undergoes fission within this loop. So we did a model for this. But fusion between ER membrane and, for example, Golgi membrane or ER membrane and plasma membrane, I never heard about it. Never heard.
I have last question. So the buckling instability for the sheets when too thick, and I mean the ratio of thickness to
buckling instability assumes that you apply forces. This is all supposed to be tension-free and load-free. And we have a good evidence for that because, for example, these tubes are loose. They are not stretched. They're just loose.
I have a biological question. Could also the lipid composition contribute to the curvature of the...
In general, yeah. I mean, in general, I skipped it, of course. In general, the lipid composition can contribute to the curvature. For that, what we need is that lipid composition of one monolayer is different from the lipid composition of other monolayer, which is not a big deal. This is what happens. We know that the cytoplasmic monolayer, for example, of plasma membrane, has a completely different composition. But we did estimations, and these estimations convinced me, at least, that in order to generate curvatures of the range I was talking about, with 10, 15, 20 nanometer radius, one needs irrealistic. For example, one needs 30% of a lipid such as DAG, diacylglycerol, in one monolayer, as compared to 0 in the other monolayer, which never happens. But in general, theoretically, it's possible. It's all the question of numbers. It's not.
So you think that the proteins just bend the membrane like mechanically, or could it be possible that they preferentially select some lipids?
Yeah, this is. They do. I mean, proteins such as epsin, for example, they do the following thing. They bind PIP2, and this is a major interaction which brings the protein to the membrane. And on top of this, it inserts its leg into the membrane, and this insertion of the leg of the amphipathic helix generates the curvature. So this is what happens in most cases.
When we first said that it's a 25 kT energy of bending, I said it's
20
purely accidental, but now since you described this active process, is it has anything to do with ATP 25?
No, this is not.
Process? I know, but
I mean, this process I described is not active. It is GTP, it is basically energy independent, ATP, GTP independent. 20 kT is the bending rigidity of the membrane. This 20 kT comes basically from the membrane thickness. Bending.
I thought you said it's the protein that control that.
Protein.
That other bending is higher in energy than.
No, I was not clear enough.
Yes.
So if we talk about the membrane per se, lipid bilayer, it is characterized by the bending rigidity of 20 kT. A monolayer is characterized by 10 kT. A bilayer by 20 kT because the monolayers can usually slide with respect to each other freely.
And on the tube edge, what would be the
25 nanometers. Not so the radius of the edge cross section is 25 nanometers. The bending rigidity is 25 kT. So one can easily calculate the energy per unit length of the edge, and this basically gives you the bending rigidity of the edge line. It comes from the bending rigidity of the membrane multiplied by the area of the membrane related to unit length of the edge line.
Can we think of a closed surface with a high genus with a line on the surface in which there's spontaneous curvature, which kind of varies, but the spontaneous curvature is zero except on the line. So it wants to be flat, but it wants to take on the line. It wants to take a curvature, and somehow the line.
Yeah.
The line. This produces a kind of an energy on the curve.
Yeah, but spontaneous curvature should come from somewhere, Charlie.
Well, it comes from the location.
In this specific model, the curvature of the line is generated by proteins.
Yeah. So, but that's right. So
the
proteins are on this. The proteins are on this line.
Yeah.
Right, and so somehow, but you could think of an energy of the kind that I've suggested.
Yeah, what we're on model-wise, we see it as the following: we have the membrane as one entity, and the edge line which borders the membrane, and the edge which borders the membrane as a other entity. The membrane edge is So, and each of them has its own elastic characteristic. The surface is the flat membrane is an elastic surface with zero spontaneous curvature, and the line along the edge of the membrane is an elastic line with its own rigidity of the line and spontaneous curvature of the line. This is what where it boils down to.
I think maybe we should now continue in the corridors and we can finish up for the event.